Hello again. Today we're gonna go over valves again, and we're gonna take a look at knowledge tree. In knowledge tree, we're gonna take a look at different type of valves. We have globe, gate, valve, control, etc. So let's get started. For globe valves, we're gonna use this type of valves we have here. These are the globe valves. And these are going to be used primarily to stop, start, and regulate flow, meaning that they're very good at throttling. And throttling basically means that you can open or close or partially open or close a valve. These glow valves, they are very, very good for isolation and throttling, as I already mentioned. So one of the things that we will need to know is in comparison to other valves, glow valve has this tortuous path compared to the gate valve. Gate valve is very linear. So this glow valve has this tortuous path and it has a larger head loss or a greater pressure drop. It also has the least linear travel compared to other valves. If you can see, this one is like more linear travel. They're good for trolling, as I already mentioned. And something important, so when this valve is open 25%, we are letting out more than 50% of the flow. That's something good to remember. And we have also gate valves, and the gate valve is generally used to completely shut off fluid flow or to be used in the fully open position and just to provide full flow in a pipeline. So we have this valve, and this valve, it has a smaller head loss compared to the globe valve. It's gonna have the lower pressure drop. It's gonna have the larger flow rate. So the flow rate is gonna be larger in here. And it has the most linear disk travel, as we can see it in here. So it's gonna be very, very linear. And something important to remember, this valve, when we open this valve 25%, we're letting out 90% of the flow. So almost of the flow goes through when we open this valve 25%. Then we have the ball valve, which is basically a shut-off valve that controls the flow of a liquid or a gas by a means of a rotary valve. And this rotary valve, it turns in a quarter, like in a 90-degree around its axis. And this way we can block the flow in this valve. So one of the characteristics of this valve is that they are very reliable and they have a very long service life. And one of the things that we need to know about this one is that when this valve is fully open, it's going to have the least frictional head loss. Then we're going to have the control valve, and the control valve, as its name says, is used to control the fluid by varying the size of the flow that passes through it. So, and this is an example. So here we can very good control the flow. So this valve, when fully closed, we're gonna have cavitation and a large pressure drop. So those are the things that we're gonna notice with this valve. Next, so now we're gonna have the centrifugal pump operating curve. And this is something that we saw in here in the glow valve and gate valve, right? When the valve is open 25%, we let out 50 to 90% of the flow, right? So when we open the valve at 100%, meaning it's fully open, we're not gonna let out twice as much, right? Because we are already letting out between 50 and 90% of the flow, so it's gonna be less than double if you can see, like in this example. It's always gonna be less than double. So now we have a problem So we're gonna go over this one is for a lube oil heat exchanger. So we have, and I'm gonna open it up in here now. For this problem, it's problem P1201 refers to a drawing of a lube oil heat exchanger. So we have here a cooling water outlet valve. So we have this heat exchanger. So here we're gonna have cooling water in and cooling water out. We're gonna have our lube oil in and our lube oil out. So this is gonna be the coolest. This is gonna be the hottest. This is gonna be the hottest. This is gonna be the coolest, right? We're just trying to transfer heat. So it's asking, so this is very important. If the cooling water outlet valve is partially closed, so if we have a valve in here, so let's assume that we have a valve here that it says is partially closed from the full open position. So we started at the full open position and then we throttle close the valve, right? We can say, oh, I throttle close 50%. So the heat exchanger cooling water pressure upstream of the valve will. So what's going to happen with the pressure upstream of the valve? So upstream of the valve, so for people that don't know what upstream and downstream means. So imagine that you have this mountain, you have a river, and you have the sea or the ocean. So this is upstream if we go to this direction, and this is downstream. Because my first language is Spanish, so to me, it was kind of like backwards. So I was like, wait, this doesn't make sense. But now with this one, it makes sense now. Okay. Coming back to the problem. So here are some rules, and we will take a look at these rules in the following examples. But for now, let's analyze this 5 steps. So we have this valve in here that we throttle close. So meaning what happens when we throttle close something? So we're basically reducing the flow. And when we reduce the flow, we're actually increasing the differential pressure. So in order to do this, our pressure downstream, it has to increase, and our pressure upstream, we have to decrease. So when we have this differential pressure increase in this valve, because we can have another valve here, another valve here, but when we are acting on the differential pressure on this valve, these ones are going to be opposite. That's something that really helps me when I'm taking like the GFEs exams, to kind of like remember. Unless they give me another type of information, I will use this rule. So now, this helps me answer actually the first part of the question, which says if a cooling water outlet valve is partially closed from the fully open position, heat exchanger cooling water pressure upstream of the valve will, so what's going to happen upstream of the valve, right? I already have my answer. So I'm going to increase, right? The pressure is going to increase. I'm increasing pressure. So now, the second part is asking me about the temperature of the lube oil exiting the heat exchanger. So it's asking me about this part. So what's happening with this oil? So since I am decreasing my cooling water, what I'm actually doing is decreasing the overall heat transfer, right? So I'm decreasing my overall heat transfer. So since I already know that I'm already decreasing my overall heat transfer, and I need to know what's happening with my T oil. So we're using the QMCP delta T basically, but we are separating into its components. So we know they're not saying anything about the flow rate. They're not saying anything about anything else. So to me, everything is constant. They're only asking me about the temperature oil out. And one of the things that I do in here, so I don't get confused and I get my arrows in the center in the right direction. So since I'm saying that this one is a constant, so I just assign a random number. So in this case, I put a 10 minus 5, it gives me 5. I know that, this gives me 5. But what happens when my goal is trying to decrease my delta t, because since everything else is constant, I need to decrease my delta t because this one is decreasing, right? So in order to decrease my delta t, I need to increase the temperature on my oil out. So I need to increase it. And the answer is yes, correct. I increase the pressure upstream of the valve and I increase the lube oil exceeding the heat exchanger temperature. So now let's take a look at another example. So we're gonna look at, so we have another example here. So we're also gonna take a look at a cooling water system with 2 centrifugal pumps. So now it says this one, it's P3901. Refer to the drawing of a cooling water system in which both the centrifugal pump A and B are operating. So we have 2 centrifugal pumps and we have them here, right? If we'll take a look at the pump operating curve. So this is in parallel, right? So I have this one here and this will be my pump A, this will be my pump E. If I have both of them running, so I will have like a higher head and higher flow than if I only had my pump A running. In this case, I only have my pump A running, so the problem states that pump B is not running. And it says, okay, yes, but it's also telling me that valve B is open. So let's take a look at what it says, what the problem says. An operator stops pump B, but the pump Bravo check valve fails to close, right? Not running, fails to close. In comparison to normal operating with only pump A running, operation with the failed pump Bravo check valve will result in pump A flow rate being what? And heat exchanger flow rate being what? Okay, so let's go back to the operating pumps. So as I say, so if we had both of them running, this wouldn't be my pump work, right? So having an extra pump in parallel will help me increase my head and my flow. But okay, now let's imagine that we only have one pump running. But this pump is not running. We're gonna have the highest head loss and the lowest flow, right? If we didn't have this one running. But since pump A is running, we are decreasing the head loss and increasing the flow, and that will help us answer one of the questions here. So flow rate A is gonna be higher than normal, right? Because we have them running, like comparing like not a pump running and then this one running, yeah, it's gonna be higher, right? So now this one, since we have this recirculation path in here, this is gonna act like a recirculation path that is gonna help us to kind of like slightly lower the overall head loss of the system, and the heat exchanger flow rate is gonna be less than normal, right? Because this is going to the heat load, so it's gonna basically go back to my heat exchanger. So I will end up having less flow rate than normal through my heat exchanger. Okay, so now next, let's take a look at another one. So now these ones are kind of important because, so we have more here, but these ones I think we can get a little confused, and there's kind of like a rule that I follow so I don't get confused with these ones. And this is basically here, is basically this part in here. This part. So we have this centrifugal pump, and downstream we're gonna have 3 valves, right? We're gonna have valve, I don't know, A, B, C, 1, 2, 3, whatever you want to name them. So for the middle pump, this is the one that we're gonna be modifying. So for this pump, we're gonna look at its initial and its final position, right? So if we decrease the flow on this valve, so if we decrease the flow in this one without knowing any other information, just this one, we are actually increasing the differential pressure. If the work is done in this valve, this pressure is going to increase and this pressure is going to decrease. So the pressure here increases, the pressure here decreases, right? We know this valve, since the flow decreases, it's going to have, the valve is more closed. Whereas if we increase the flow in this valve, which we are opening the valve a little bit more, that's how we increase the flow, we are decreasing the differential pressure. So these ones are kind of like opposite. Also, these ones are opposite, and these ones are opposite, as you can see. So in here, since in this one, the flow increased, meaning we open the valve more, the differential pressure decreases, meaning that this pressure decreases and this pressure increases. So this one has the same direction, this one has the same direction. This one has the same direction, this one has the same direction. I don't know if that helps you like remember. So now, there's going to be certain cases where they ask you or they give you more values, or they ask you what's going on with the valve upstream or downstream, right? So that upstream or downstream. Okay, so if my differential pressure decreases and my flow decreases, that means that these ones are going to go to the same direction, up or down. We don't know yet. We need to have more information in order to know if it's going to be the valve, if it's going to be upstream or downstream, right? And we will take a look at those ones. So this is going to be the first one, which is P6601. So this one is telling us subcooled water is flowing through a throttle valve in an open system. The initial steady state conditions for the throttle valve are as follows. The inlet pressure, we start at 60, and the outlet is 44. We have a dP of 16 with a flow rate of 800. Now let's compare it with the current steady state conditions. The current steady state conditions, we have the inlet pressure increased and the outlet pressure increased. My dP decreased. So since I know that my flow rate decreased, this is telling me that somewhere this valve was closed. I just need to figure it out where. Okay, so I got my flow decrease, my differential pressure decrease, right? Then I have that my pressure in and pressure out, they both increase. So this is telling me that the valve that was closed was not the valve that I'm working on. It was the valve downstream, right? When this goes up is the valve downstream. When these both go down was the valve upstream. So now let's take a look at this other one. This other one I got a initial differential pressure of 16, so my dP increased, right? So I got a increase in my dP, but I got a decrease in my flow. So that's telling me that since my flow decreased, somewhere this valve was closed, but I have this one's opposite, so that means that the valve that was closed was the throttle valve. So was the valve that I modified. It was the valve in the middle. It was this one. Okay, so now let's take a look at the next one, which is a similar one. So this one is giving me differential pressure initial of 16 and next dP or current dP is 9. So I had a decrease in my differential pressure. I had a decrease in my flow. So from this information, I know, okay, this is not normal. So that means that we are not doing anything on the current valve or the middle valve. Since I know that the flow decreased, I know that somewhere a valve was closed, but I know that it was not the middle valve because this one's going the same direction. So since my pressure inlet and outlet decreased, pressure in and pressure final decrease, so that means that I know my upstream valve was throttle. This direction is telling me, okay, it's the upstream valve that was throttle. So what's this one? This is my upstream valve. This is upstream. Sorry, it's backwards. This is my upstream valve. So this is the valve that was partially closed. And now we're gonna have this other example. I think it's not the last example. So we are gonna have a differential pressure initial of 16, and then we're decreasing our differential pressure. So this is interesting because here is telling me I had an increase in my flow. So if I had an increase in my flow, somewhere a valve was open, right? Somewhere a valve was open, my differential pressure decreased, so these are opposite. So the valve that was open was the valve in the middle, right? So here says the throttle valve was open more, and yes, it's this valve in the middle, that's my throttle valve, that's the valve that I'm working on. That's gonna be this one. It was not a valve upstream or downstream, right? It was my valve that I'm trying to work on here. And then let's take a look at this one. This one is interesting. And I think I have it in here. I explain it a little bit more here. Let's use the same logic, or let's try to use the same logic. Here we are not having the flow, so we have to rely on what we know. So we know that if we decrease the differential pressure, we're gonna increase the flow, right? That's kind of like what we know. And we know that if the pressure inlet and outlet are different directions, that means that we're working with the valve in the middle, right? So that means to me, okay, so we open the valve, like we have more flow, this valve was more open. So let's take a look at the options, because here the answer to me, it will be that I open this valve more, right? So valve B, if I analyze things this way. But if I go to valve B, it says the valve B was closed more, and that's not the answer. So I'm like, okay, so this is not the answer. So then, since I really don't know, because it's not telling me anything about the flow, like I really don't know. I don't know exactly what's going on. So now, it's giving me another option here. It's telling me that valve A was open more, right? But if valve A was open more, these directions would have go the same direction, right? But they go in different directions. This one's, if either valve A or valve C would have been more open, in reality, this one would have go the same direction, but it's not the case. So I know that valve A and C are not the answer. So now the only answer that I have is gonna be D. It's gonna be that this valve up valve B was open more. And that's actually gonna be my right answer for this one.